continue.
Okay, for our next lecture, we are continuing with the course by Zohar Komargodski about topological operators and defects in quantum field theory.
All right, so let me just recap the last lecture. So we said that anomalies in quantum mechanics can be understood as the fact that fusing symmetry operators leads to some funny phase, which cannot be removed by redefining the operators individually. And that's classified by some cohomology group. And that means that wave functions are in projective representations. And that means that there is a degeneracy. So I'll put another. So there is a degeneracy in the ground state in quantum mechanics, and it cannot be removed by instantons. In quantum field theory, 't Hooft anomalies are labeled by something much more abstract, which is some higher cohomology group that's very difficult to describe. It's not just projective representations. And there is a big conjecture in the field, which I try to give you some arguments for with this weak rotation. These arguments are not a proof by any means. They're just maybe motivation, maybe inspiration. You can call it whatever you want. The conjecture says that if a quantum field theory has an anomaly, then there is no simple is a technical word that means one superselection sector. No simple symmetry preserving boundary condition. Now, usually people talk about anomalies as a problem with gauging. Maybe you heard this perspective that you cannot gauge some symmetry, but gauging a symmetry is not an experimental operation that we can do, while trying to put a boundary is something very physical. So it's just a very clear practical statement of what it means to have an anomaly. And probably, most likely, the correspondence goes both ways. Okay? So we believe this is a complete characterization. It's a big conjecture, not proven. Try your best to prove it. Okay. Now I'm going to show you examples of how it works. It's quite interesting and simple examples to see how it comes to life. And then I will make contact between this big conjecture and the space of theories. So it turns out that boundaries, and more generally defects, as we will see later, are a very important tool to try to understand the space of theories, the space of all possible quantum fields. So for now, let's just warm up and do some examples. Yeah. Yes. Oh, you need a microphone. Is there? Just a second. For the recording's sake, you need a microphone.
Does putting boundary conditions introduces new fields into the theory?
Yeah, anything you want. So when we say, people when you have a piece of material, you want to put a boundary condition, you're allowed to put you're allowed to put a red color on the boundary, blue color, anything goes. When we say boundary condition, literally I mean anything goes. You can do whatever you want as long as you can end the system. And on the other hand, on the other side of the system, there is air, like nothing. Air is like nothing. Trivially gapped phase, okay? So boundary condition doesn't have to be just like restrictions on the values of fields at the boundary. It could be, you could put anything you want in the boundary and couple it in any way you want to. So it says that there is just no way, however you do it. Okay? So I think this is a very practical, this is a very intuitive meaning for what it means to have an anomaly, because it means that there is no way to end the system in a symmetric fashion. Do I think this conjecture is correct? Yes. Are there proofs? Maybe in special cases.
I was asking this because if you gauge this symmetries, you'll have these ghost fields, right? I was thinking putting boundary conditions has this, it requires you to have additional fields if you put just
yeah, when
fields.
I say boundary conditions, so here G is a global symmetry. And I mean, there is no way to preserve G in any way of ending the system. Okay? I don't know, I'm not trying to gauge anything. It's not an operational thing to gauge. Okay? So this is a big conjecture. And I'll show you that it's connected to very deep questions about the space of theories very soon. But now, just to warm up, I'll give you some examples of how it comes about, how this conjecture comes about, in simple examples. So let's take a 1 + 1 dimensional theory. And before I go to the first example, let me just even extend the conjecture a little bit. So I motivated the conjecture for global symmetries, but people in the community believe that this conjecture is true even for space-time symmetries. So in particular, look, another consequence of that, if you extend it slightly, is that if a theory has a 't Hooft gravitational anomaly, so you might have heard that some theories have gravitational anomalies. This is like a space-time anomaly in diffeomorphisms. Then what would be the analog of no G-preserving boundary condition? Now G is essentially the space-time symmetry. So the conjecture is that there is no boundary condition whatsoever. So a theory with a gravitational anomaly cannot even end. You cannot put it on a half space-time. Okay? So that's an extension of this general philosophy or this general dogma. So let me start with some examples. So let's take a 1 + 1 dimension. Any other questions? Yes.
In the last lecture, you said that the weak rotation is related to the giving the boundary condition. So could you clarify how they are related together?
Yeah, okay. So in the last lecture, I spent 15 minutes trying to motivate this conjecture by using this picture from quantum mechanics that we can create states by path integral evolution and states transform projectively under symmetries. And then I did some weak rotation, okay? This was not a proof of, it was an attempt to motivate the conjecture for you. It's the best I can come to a proof. I don't have a proof. I would publish it if I had a proof. But this is the best argument I have, you know? Okay? So if you don't find the argument convincing, I agree with you. I also don't find it convincing. But it's the best I have.
Sorry, I'm not sure I understood the gravitational anomaly case. So there, the group is gauged, and
The group is what? No, it's a quantum field theory with a 't Hooft gravitational anomaly.
at fixed. Okay.
I'm talking about quantum field
So
theory,
you're
not
not-
quantum graph. I'm
you're-
talking about quantum field theory in D+1 dimension with a gravitational anomaly.
You're not allowing anomaly inflow. Anomaly inflow, you're not allowing any anomaly inflow.
This is just quantum field theory with gravitational anomaly. This is what used to be called the Alvarez-Gomez-Witten anomaly. Like global quantum field theory, no gravity, but that cannot be coupled to curved space in a diffeomorphic invariant fashion. Okay? Any other comments before I go to simple examples? So the first two examples will be semi-trivial, and the last one extremely fascinating. And it led to at least 100 papers over the last 5 years. So the first example is just a chiral fermion. So I take a fermion that's right moving. So in 1 + 1 dimension, there's a quantum field theory for a fermion that's moving to the right. And there is no fermion that's moving to the left. And it's going to be a complex fermion, okay? That's why the plus just means that it's moving to the right. Plus is to the right. So this is the Lagrangian. It's a single complex fermion that's moving to the right. And now we're trying to put a boundary condition for the system. This system has an Alvarez-Gomez-Witten anomaly, so it has a gravitational anomaly, because the gravitational anomaly in 2 dimensions in general is the difference between the central charge of left-moving modes minus the central charge of right-moving modes. And for this theory, it's 1, because I have a single minus 1. I have a single degree of freedom that's moving to the right. So this theory has a gravitational anomaly. And it should be obvious to you that there is no way to put a boundary condition. Because what would you do after this fermion hits the wall? It cannot bounce back because there is no quantum mode in the Fock space that moves to the left. So there is no sensible boundary condition. Is that clear? So this is the simplest example of what I said. There is a gravitational anomaly. There is just no boundary condition. Is that okay? So the next example is when you have one left moving mode and one right moving mode. So now we have a quantum mode that can move to the left. And now we can put boundary conditions. So when a right moving mode strikes the wall, we can write a boundary condition where the mode would come out of the wall. Okay? And there are two types of boundary conditions you can write. You can say that the right moving mode is equal to the left moving mode when it strikes the wall. Or you can say that the right moving mode is equal to the complex conjugate of the left moving mode when it strikes the wall. These are two simple boundary conditions you can write. Okay? The symmetries of this system, what is G? The symmetry G of this system is U1 times U1. The first U1, let me just write a table. So we have a U1 times U1 symmetry. And we have two fermions, psi plus and psi minus. So the charges are 1, 1, 1 minus 1. So this is called vector, this is called axial. It's just notation. So you see that this boundary condition preserves U1 vector, but it violates U1 axial. And this one does the opposite. This one violates U1 vector, but it preserves U1 axial. Okay? And indeed, this is compatible with the general theorem or the general conjecture about boundary conditions, because if you calculate the anomaly of the symmetry G, so it's classified by H3, G, U1, and you need to calculate the anomaly in this particular model, what you will find is that the anomaly of U1 vector, so, okay, let me just calculate. This is the anomaly that you've seen in graduate school. These are these famous triangle diagrams, except that here in 1 + 1 dimensions, these are just vacuum bubble diagrams. So this one doesn't have an anomaly. So the axial U1 is non-anomalous. The vector U1 is non-anomalous. I'm just repeating the anomalies in 2 dimensions for chiral fermions. But this diagram is 1. I'm just using some convenient normalization. So there is a mixed anomaly between axial and vector symmetry, but no self-anomalies. So what does that mean? It means that you cannot preserve both U1 axial and U1 vector. You can preserve one, but not the rest. So if you ignore the U1 vector symmetry, you can preserve in a boundary condition the axial symmetry. Or if you ignore the axial symmetry, you can preserve the vector symmetry, but you cannot preserve both. Okay, so this is another clear demonstration of this kind of general conjecture. Are there any questions about this example? Good. And now, one more example that is a little bit less trivial. So here, I guess it's clear. You send the psi mode, some psi mode comes out. You send the right moving mode, the left moving mode comes out. And now I'll show you an example that is really baffling, but true. So now we'll take a system of 2 right moving modes that I will call psi plus and psi plus prime, and 2 left moving modes that I'll call psi minus and psi minus prime. And there will be a single U1 symmetry. There will be a single U1 symmetry with the following charges. So this will be 3 and 4, and this will be 0 and 5. So these are the charges under some U1 symmetry of right moving and left moving modes. In the literature, this model is called the 0-3-4-5 model for obvious reasons. Why did I choose these funny charges for left moving and right moving modes? I chose these funny charges because 3 squared plus 4 squared minus 0 squared minus 5 squared is 0. And that guarantees that the U1 anomaly vanishes. So that guarantees that this diagram vanishes, because the anomaly in 2 dimensions is the sum of charges squared of left-moving modes minus the sum of charges squared of right-moving modes. And so if we believe this general conjecture, there must be a boundary condition that preserves this U1 symmetry. So if you send a mode that comes out must respect the symmetry. And you would think, how is that even possible? I can send an incoming mode with charge 3. So I can send this mode from the Fock space with charge 3. How the hell can it bounce off the wall and come out? There is no way to preserve the U1 symmetry. The only available left-moving modes have charges 0 and 5. And you cannot make a 3 out of 0s and 5s. So even if you build a very complicated state in the Fock space, you will not be able to conserve the U1 symmetry. So then your conclusion must be that this general conjecture is wrong, because in this model the anomaly vanishes, but clearly there cannot be a boundary condition that respects the symmetry, right? Because there is nothing that can come out that would add up to charge 3. So this is called the unitarity puzzle. In the literature, some people call this the unitarity puzzle, because there should be a boundary condition, but you cannot write a boundary condition that's linear in the fields that makes sense. Okay. Anybody has some suggestions of how to proceed? What can we do should we throw the conjecture to the garbage, or? Huh? Yeah, that's right. If you send 5 Fock space states with charge 3, then you send in 15 units of charge, and then you can have 3 units of left-moving charge coming out, and the symmetry is preserved. But what if you don't want to send 5 units of the quanta, but just 1 unit of this quanta? Okay. So this is a very deep puzzle, and it turns out that the resolution is the following. First of all, I'll just tell you the facts. Fact number 1 about this problem is that I'm looking for the eraser. So fact number 1 about this problem is that there is a boundary condition. So fact number 1 is that there is a boundary condition, and it completely agrees with the general conjecture. Fact number 2 is that there is a way to scatter a particle of charge 3, and something comes out of charge 3. So it turns out that if your only quantum modes are fermions with charge 0 and 5, you can still make a very complicated state in the Fock space, which has essentially 0 energy, but it has charge 3. So a charge 3 mode can be made. This is one of the magics of massless quantum fields. Massless quantum fields behave in a very unintuitive fashion. But you can make a charge 3 mode that's moving to the left from charge 0 and charge 5 modes. You just have to make very complicated Fock space states that consist of infinitely many particles. Okay? So the unitarity puzzle is solved by preparing these extremely complicated states and constructing the boundary condition. And these things have been done by now even numerically. There is a numerical simulation that shows that this boundary condition exists. Okay? So one lesson you can draw from this is just a tangential remark for you, is that for the S matrix in massless field theories should be regarded with maybe a good chunk of skepticism, because you see that the Fock space is definitely not enough. In this simple example, it's clear that the Fock space does not describe the S matrix. You need to go beyond the Fock space and prepare some very complicated states. Okay? Any questions about it? Yes?
Can we have a boundary condition like psi plus is equal to 3 by 5 psi minus?
Want to make psi plus equal what?
5 by 3 or 3 by 5 psi minus. Or, sorry.
Psi plus equal to? Oh, you want to say that psi plus is equal to psi minus prime to the power?
Times 3 by 5.
Times 3 by 5.
Yeah.
No, what is this? This doesn't, like, no, this is nothing, no? What is this? You can just rescale the fermion by 3/5. It doesn't do anything. The charge of this mode is 5, and the charge of this mode is 3. The fact that you multiply it by a rational number doesn't do anything. I thought you wanted to raise it to the power 3/5, to take a fermion field to a fractional power. Then at least the charges would work. But what is that? Right? That's the exponential of a fermion. Well, what is that? So you cannot write a boundary condition. Nobody can. But it exists, and it was shown numerically that it exists.
Sorry, quick clarification. You're also assuming that the boundary has no sources.
You can, sources. You mean external sources? Like
Yeah, some
somebody's
sources on
pumping
the
energy.
boundary. Yeah.
Yeah, I want this to be a closed quantum system. Closed quantum system. So that's my only assumption. I don't want a time-dependent Hamiltonian. Or I don't want the Hamiltonian to be in a density matrix. I want like closed quantum system. But other than that, I'm not assuming anything.
Following up on his question, I mean, could the boundary tier, there be a boundary tier that can store charge, and then what comes out is a different charge because the boundary, there are some fields at the boundary that can store charge?
Yeah, that's an excellent point. I'll say something about it. So Francesco's comment is that maybe if you send in charge 3, it's trapped to the boundary and it never comes out, right? That's a possible resolution of the S-matrix unitarity puzzle. So there is a small thing that you can prove. You can try to construct something like that, and you will not succeed. I'll tell you now why. There is a small thing that you can prove, which is that for very low frequency fluctuations, there is no way to store charge because they kind of want to escape from the boundary because of the large Compton wavelengths. So a more mathematical way to say it is that at the low energy limit, this has to satisfy the Cardy conditions. And you can prove that if something satisfies the Cardy conditions, the charge density of the boundary cannot have a delta function. So there is a mathematical proof of that shows that there is no way to do that, what you said. It's a good idea. You can do that for massive particles. You can capture a charged massive particle, but there is no way to capture a charged massive particle, essentially. This was proven rigorously in some paper of Herzog from a few years ago. And I use it all the time in various arguments. Yeah. So I think it can be ruled out.
This, just to understand, like the fact that we are placing the wall on the right is a constraint or a choice?
I just chose it like that.
Meaning, like going back to the earlier thing, if I were to place the wall to the left,
it doesn't matter. It doesn't
only
matter.
have a right moving
you can place a wall to the left. You'll have similar unitarity puzzles.
It's not so much a unitarity puzzle here. I was not referring to this, but rather the notion that we necessarily need also a left mover in the first place. Like I guess that in the end there will also be issues in placing the wall on the left and evaluating the behavior of the psi right on the left wall.
Yeah.
But, so I guess.
Yeah.
But so the question was more like when we establish this kind of conjecture, we are also allowing ourselves to place the boundaries wherever we want.
Yeah.
Okay.
The statement is local, that there is just no boundary condition. It doesn't matter where you put it.
Okay.
So, what does this teach us? Because this felt to me like this could work as a counterexample. This is something that doesn't have an anomaly, and it looks like there is no way to solve it, and there is like some very, very complicated way to actually show.
Yes, this shows that the conjecture is very likely to be true. Because in the simplest case where it could have failed, it was saved miraculously.
Okay.
So sociologically, it plays a big factor in making you confident. So people thought, okay, there is no way, and then the boundary condition appeared, And the scattering problem is solved by showing that you need to scatter something not in the Fock space, and everything's fine. So,
I just wanted to ask, does it work for any Pythagorean triple, so to speak?
yes, it does. It works. Like you could try to construct more complicated. Okay, Kentaro found an example where nobody yet found a solution. He has a paper about it, right? You didn't publish it? No, Kentaro found a configuration of charges that nobody has been able to find the boundary condition, and according to the conjecture, it must exist, right? Yeah, he has infinitely many examples like that. Yeah, so I also wrote a paper with David Tong, where in the last section we have an example that nobody knows how to construct a boundary condition to, with David and Philip and Marieke and Diego. And so, yeah, this is a miracle. The fact that this was found is a miracle. But we learned a great deal from it about scattering of massless particles. Clearly, scattering of massless particles is not done in the Fock space. So you cannot make sense of it in the Fock space. Okay? But yeah, there are more complicated examples with the Ramanujan's numbers, and like, nobody found how to save it. Nobody found the boundary condition. Okay, now I shall continue to the consequences of this statement for the space of quantum fields. So one famous consequence of anomaly. So if you learned anomalies, like people traditionally teach anomalies, that if there is a 't Hooft anomaly, then there is the theory cannot be trivial. It has to be either gapless or break a symmetry. So let's try to derive it from this perspective, that no boundary condition exists. So I want to show you that these ideas are all interconnected. So suppose you have some quantum field theory in D+1 space-time dimensions, and you could gap it. So somebody found a way to add an operator, integrated operator, of course, such that the infrared limit is gapped. So that means that if there is some global symmetry G, and this is a G invariant deformation, there should not be an anomaly according to our old ideas about gauging. But now let's see how do we understand it from the conjecture about boundaries. So consider the following construction. We take space, let's say space is two-dimensional, and we take some region in space, and in this region of space, we add our deformation, and in this region of space, we don't add the deformation. So now we flow to the deep infrared, and if indeed this deformation leads to a gapped phase, by locality, it means that in the infrared, we've created a boundary condition. Okay? Is that construction clear? Sometimes people call this construction RG-induced boundary condition. So it's a renormalization group that dynamically leads to a boundary condition. A renormalization group flow that leads to a boundary condition, okay? So what did we prove? This is a picture, but it proves that any gappable theory cannot have an anomaly because it has a boundary. So we've proven that if a theory is gappable while preserving G, we need to preserve the symmetry G. Otherwise, why did I need to preserve the symmetry G? I need to guarantee that this boundary condition is G symmetric. Because if I gap the theory while violating G, this boundary condition will not be G symmetric. So I proved that if a theory is gappable preserving the symmetry G, that implies that there is a boundary which preserves G. And that implies, according to our conjecture, that's our conjecture, that there is no anomaly. And that's one of the main hallmarks of anomaly, that if you know that there is an anomaly, there cannot be a gap. a trivial gap. So now we've proven the same through the construction of an RG-induced boundary condition. Is that clear? Is this construction clear? And a big conjecture is that all these arrows go the other way. So, and this becomes a very powerful statement about the space of all quantum fields. So you must believe that every theory that has a symmetric boundary is also gappable. Okay, so let me just write it. That's another big conjecture in the field, which states the following. So every system that is gappable, so I'll just write G preserving like that. Every system that's gappable preserving some G has a G preserving boundary, and the opposite is true. And that leads to some big structural, and this is the same as anomaly. So no anomaly. So no anomaly for G, okay? So all these ideas are connected, and it leads to some very interesting statement about the space of quantum fields. Let me draw a picture. So let's say this is the space of quantum fields. So this statement says that there are different circles with quantum field theories that are continuously connected by deformations. The deformations are always G preserving. So you take any quantum field theory that you like, you start adding G preserving deformations, and you can move in this circle. So there is one special circle that's characterized by having no anomaly. That's this circle, no anomaly, and having a boundary condition. And we claim, what does this conjecture mean? It means that all the theories that have no anomaly or that they have a boundary condition are continuously connected by deformations. And that's a big conjecture in the field that says that essentially boundary conditions, having a symmetric boundary condition kind of characterizes the theory. Okay? So we see that like boundary conditions on the one hand sound like a very practical thing that you need to worry about if you have a finite system. On the other hand, they capture a lot of information about anomalies and topology and these kind of things. So that's the first message. Are there any questions about it? Maybe I'll add one more thing and I'll finish about this particular topic. This set of conjectures is part of a field that's called SMG, a symmetric mass generation, which is just the statement that every theory which has no anomaly must be somehow gappable. That's what this field of research is about. So in particular, this model must be somehow gappable. Now, if you are a continuum quantum field theory person, it's not obvious how to gap this theory. If it was obvious, we could have easily constructed a boundary condition. But it is possible to gap this theory, and it was shown on the lattice that it's possible to gap this theory by sufficiently complicated irrelevant interactions that go to strong coupling. Okay, so this model is gappable by adding various irrelevant interactions that become very strong.
Zohar, one
Yeah.
question. So theories with gravitational anomalies can't have boundaries,
Cannot have any boundary.
so they can't be gappable?
They cannot be gappable.
Okay,
Theories with gravitational anomalies cannot be gappable.
okay, thank you.
Now, any other questions about this set of claims? Good. So, yes. Okay.
So the statement is that there is some way to gap the system, but it's not clear. I mean, it's not clear within which framework. So either lattice or QFT or some other way of defining it.
Let's say it's just a picture, no? Let's say you look at the space of quantum field theories. So one point in this space is the 0345 model. according to this set of ideas, it must be gappable. And people already know that there is a boundary condition, and they've seen that it's gappable on the computer. But in quantum field theory, if you start writing relevant operators, there is not a single relevant operator that you can write except for the mass. There is not a single relevant operator that you can write because left and right moving fermions don't have aligned charges. It's a chiral theory. So as a quantum field theorist, you would say it's not gappable. What are you talking about? But the point is that, there could be some theory up here, some quantum field theory up here. This axis is like the space of our G flow, which could flow to the 0345 model, but it could also flow to a gapped phase. That could happen. And then you could say, I can start from the 0345 model, add some irrelevant operators that would take me up the flow, and then maybe send me to the gapped phase. It's like there is some potential barrier, you could say. So you need to go up the RG flow and then maybe then come down. So there is an RG flow, it's just not, you're not flowing to the infrared. You have to first flow to the UV, to strong coupling, and then get to the gapped phase. And so the construction could be very complicated, but it should exist. That's what these conjectures predict. And indeed, it does exist in the 0345 model. You can like write sextic and quartic interactions between these fermions and go up the flow a little bit, and then go to a gapped phase. And that's how people can construct the boundary. You just gap it on one side. So you do this construction starting from the QFT in the UV. On one side, you flow to 0345. On the other side, you flow to a gapped phase, and you end up with an infrared boundary condition for the 0345 model. Okay? Yes?
Conjecture is for 2 dimensions or for any
dimension?
Any dimension.
The conjecture is for any dimension.
Even in very high dimension that people think that there are no like examples of interacting things or?
Yeah. Yeah, if there are no examples, the conjecture will be correct in an empty fashion.
But you are saying that all theories with the same group of symmetries are connected to each other?
Yes, yeah. Essentially, the big conjecture is that any two theories with the same anomalies and the same symmetries must be connected continuously. And if you just accept that big conjecture, everything I said follows. That every theory that doesn't have anomalies has a boundary because there is an RG flow of this type. You see? Yeah. So if you just make this one conjecture, there are so many interesting consequences that you can explore.
But I mean, for example, I have a symmetry between free fermions in higher dimensions and a symmetry between free scalars in higher dimensions. How can I connect them?
No, it has to be theories in the same dimension.
No, in the same dimension, but one is a free scalars and one is free fermions.
No, but look, those are not going to be in the same symmetry class because one of them might have fermion number, the other doesn't have fermion number.
Okay. The full symmetry.
The statement is that if the symmetries coincide, let's say bosonic theories, if the symmetry group of two bosonic theories coincides and the anomaly coincides in the sense that of this cohomology group is the same, the representative is the same, then there must be a continuous deformation. And if you accept that claim, there are many consequences. That there must be an interface between every two such theories, that every gappable theory has a boundary, that there must be an RG flow, many things follow. Including that the 0345 model has a boundary condition, and so on and so forth. But yeah, this conjecture is very far from being proven. It's like a statement about the space of quantum field theories, saying that pi zero of that space, just the space of connected components of quantum field theories, is equal to anomalies, right? It's like saying, roughly speaking, it's like saying that pi zero of the space of quantum field theories is the same as the space of anomalies. So it's a big claim about the topology of space of quantum field theories. You can ask, what is pi 1? That's connected to maybe other defects. This just, this pi 0. Okay? Okay, any last questions about this topic? Okay. So this was some kind of motivation to show you that defects or boundaries, they are important for conceptual questions. So now I'll talk a little bit about a different kind of defects, not boundaries, but point-like defects. They also have various interesting ramifications. So now the setup is going to be the following. We will take some quantum field. Let's say we're going to be, for the rest of these lectures, including tomorrow, I'm going to be in 2 + 1 dimensions, just for concreteness, from now on. So this is space. This is space. And we will discuss the following general problem. Let's say that we have a Hamiltonian that we can derive from some quantum field theory in 2 + 1 dimensions. And we will discuss what happens when we add some impurity. Or that's a condensed matter language. We can say line defect. Line operator. That's more a high energy physics language. Line defect. So in space, it looks like a point. So we take a point in space, and we just put some garbage there, some piece of garbage, and we ask what is the long distance. What happens when we start measuring stuff here, far away from the garbage? That's more like the actual practical question that you might ask. In space-time, it looks like a line defect, right? Because a point in space becomes a line defect in space-time. And that's why I use the word line defect here. So we're going to basically study a little bit line operators. We're going to study line operators in 2 + 1 dimensions. I already talked about surfaces in 2 + 1 dimensions. These are boundaries, essentially. So we talked about boundaries. So the next thing is to talk about line defects. So I'm going to tell you a little bit about what's the role of line defects in 2 + 1 dimensions in condensed matter and in high energy physics. Okay, is the question clear? So that's the setup. So first, we have to understand what happens to the symmetries. One important thing that I've emphasized many times is that if we have a local operator in the bulk, away from the impurity, it transforms under global symmetries linearly, non-projectively. So now, this is space-time. So we have operators that sit away from the line defect, and we have special operators that sit on the line defect. So their x-coordinate is 0, but they depend on time. An interesting general question is to understand what is the relation between these two sets of operators. The operators that sit on the line defect have nothing to do, in principle, with the operators that sit outside of the line defect. They don't have the same scaling dimensions if there is conformal symmetry. They don't have the same quantum numbers. So in the theory of quantum field theory with a line defect, we have 2 sets of operators, even 3. You'll see one more set coming in soon. And one question that we must immediately ask, these transform linearly under the global symmetries. Let's suppose the Hamiltonian for the impurity preserves some symmetry G. So this is G preserving, and this is G preserving. So we can ask, what are the transformation rules of these operators O hat on the line defect? And what I'm going to show you now is that these operators also transform linearly, non-projectively. This will be important later. So what we do is that we consider this charge. This is the charge corresponding to the element G, and this is the charge corresponding to, let's say this is G minus 1. This is the charge that corresponds to the element G. And we can try to sandwich these 2 charges near the operator O hat, and we will get a new defect operator, O hat prime, at 0t, which is given by G minus 1 O hat 0t G. So this is not going to fill any projective representation, but it could. But the following could happen. So when we consider this symmetry generators. Let's say this is H, and this is G. So it could be true that there is absolutely no anomaly in the bulk. So let's assume that the quantum, just for simplicity, let's assume that here there is no anomaly. It's a gappable model, and everything is pretty simple about it. It could still be true that while the bulk has no anomaly, when you try to fuse these two symmetry generators together, you will find some extension phase omega, like we had before. So it could be that you will get H times G, but there will be another phase, omega GH. That could be. So while there may not be an anomaly in the bulk, just introducing an impurity could, in the back door, introduce an anomaly from the phases that are acquired by intersecting, from the phases that you get by intersecting the impurity with the charge. Even if the impurity is symmetric under G, there could be an anomaly that's induced by the impurity. So this is some kind of 't Hooft anomaly of a system with an impurity. I don't know if there is a name for that in the literature, to be honest. But this could be like a 't Hooft anomaly of an impurity. I don't know if this is a standard name. But maybe 't Hooft anomaly of a line operator or 't Hooft anomaly of a line defect. I'm not sure. Is there? I don't know if there is a standard name. So this could happen. And even if the original system was trivial and no anomalies, the line operator could introduce an anomaly in the back door. So as in quantum mechanics, the operators that sit on the impurity, you see when you put an impurity or a piece of garbage in a quantum system, there could be many degrees of freedom due to the impurity that are not present at a generic point in the bulk. So the space of operators at the impurity could be very different from the space of operators in the bulk. But those operators still must transform linearly, even though there is an anomaly. As in quantum mechanics, this anomaly affects operators where the impurity appears at some moment in time. I'll discuss it now. There was a question, so I'll
yes.
stop.
Is this anomaly inflow? In the sense it is the bulk that
well, here the
bulk,
is, let's say, 2 + 1 dimensional, and the line defect is 0 + 1. So it's not anomaly inflow from the bulk, no. It's anomaly inflow from somewhere else, not from the bulk, from some additional external dimension. I don't know if there is a standard name for that, but it's a very common phenomenon that has many consequences. That a line defect introduces an anomaly. Yeah. Okay, so the operators that sit on the impurity don't feel this anomaly. They still transform linearly. But as we learned in quantum mechanics, what do we have to do to see the anomaly acting on something physical? Yeah, but here it's even more interesting. It's not just a Hilbert space. We have to make the line end, right? So this is our impurity. And now it has a different interpretation than in quantum mechanics. In quantum mechanics, this was interpreted as a state in the Hilbert space. But now the bulk exists always. There is a bulk here, there is a bulk here. It's just that there wasn't an impurity. So what's the name when we created an impurity at t = 0? It's a quench. And these operators, the operators on the line are called O hat. The operators in the bulk are called O. But we need to invent a new letter for operators that create the impurity at t = 0. Let's call them O double hat. Okay? So these operators do transform projectively, and they're called quench operators. So we can call them quench operators because what they do is that if you act on a quantum system with a quench operator, it will create an impurity for you. It will put a piece of garbage at x = 0, at t = 0, and then the system will react to it. But the quench operators, as we learned from the quantum mechanics, they transform projectively, while the line operators and bulk operators transform linearly. So the quench operators are the ones that transform projectively, okay? And my point will be tomorrow to show you that just this fact leads to very powerful theorems about pieces of garbage in very simple systems. You can prove that some very innocuous looking pieces of garbage in a magnet actually have a projective representation, and you can prove theorems that they cannot disappear, even at strong coupling, and so on and so forth. Okay, but yeah.
So this impurity cannot be detected by any other operator, say a loop operator that surrounds it?
It could.
It can be?
Yeah, so like it could be, I'll show you like, probably I'll start showing you now.
But then, yeah, then I'm asking indeed what really happens on the surface when you act with this quench operator.
So this quench operator creates an impurity.
But it has to be doing something non-local then?
It has to be doing something non-local. I don't know. I don't think so.
Because indeed, if I can measure the presence of the impurity by a loop operator around it, then I can lower the loop operator, and then at the moment that it crosses your spatial slice, it suddenly has to sort of
I see what you're saying. So that's not going to be possible. Yes, you can measure the presence of the impurity starting from t equals 0, not just with loop operators. You can measure the magnetization. It could be some magnet with some piece of garbage. You could measure the magnetization. You could measure the energy density, and you'll see that you've created an impurity.
But then your O double hat is then not literally a local operator.
O double hat does not exist in its own right. It's connected to a line operator. Right. It's an endpoint operator. So it's not something that we can act on a quantum system in and of itself.
Right.
If you act on the quantum system with O double hat, you created a piece of garbage at x equals to 0. And this piece of garbage is not mobile. It's not like when you act with an operator on a quantum system, you create an excitation, and the excitation can start moving. O double hat creates a piece of garbage that's immobile. It's a line defect.
Yeah, but often, at least, if the defect can be measured by something else non-locally, then this thing has to be connected to a string that also goes off to infinity.
Yeah, you're right. In many systems, you can ask, can we create any piece of garbage with some O double hat? So there are some pieces of garbage that can never be created. And those are the ones that can be detected by a topological line operator.
Okay.
But I'm talking about magnets here. They don't have topological line operators, and every piece of garbage can be created with O double hat.
Okay, so
in more complicated gauge theories, there are some pieces of garbage that cannot be created with any operator. And so sometimes it can happen that there is no endpoint. But I'm not going to talk about these examples today or tomorrow.
Zohar, so you just proved you showed us that even if there is an anomaly, the local operators typically transforms linearly. Now this quench operator is an exception. So
yes.
I will understand in case of a Wilson line, because this would be a non-gauge invariant because it has two leaves attached to a line. Is this what
gauge
you mean?
invariant. Why not gauge invariant? Oh, it's fine, it's gauge invariant.
Well, if it is only leaving at the end of the line, it might be what we call it a non-genuine operator.
Yeah, let's say for gauge theories, a familiar example of a line operator is the Wilson line, which is the piece of garbage where you put a nucleus at the origin, right? It just describes a heavy nucleus at the origin. And this can be created by an operator such as the electron field. Let's say it can be created by the electron field at equals to 0. Right? And then it's connected to a Wilson line like that. So that's an example. But it's perfectly gauge invariant. You just put a nucleus at the origin. And I should put two hats on it because it's my defect creation operator.
Yeah, no, what I mean is that psi hat formally in the Hilbert space does not give rise to a gauge invariant operator.
Correct.
It's a non-gauge invariant local operator. Together with the line, it is fine.
Yeah, and what does it do? It puts a nucleus at time t equals 0 in the middle of the sample.
But is this why these quench operators are special in the sense that they are allowed to transform projectively in contrast to,
so
to
if
what
you
you
like
said
gauge theories,
in the morning? Yeah.
if you like gauge theories, it's very clear that they're allowed to transform projectively, because in gauge theories, these are what we usually call non-gauge invariant operators. Of course, they are gauge invariant, but that's why they have finding quantum numbers.
Okay, yes.
In condensed matter, they say they're fractionalized.
Yes, thanks.
There's
So my question is, should I think of this O hat? So as you said, I guess we are making the implicit assumption that any H impurity can be associated to some creation operator of sorts.
Yes.
But like the fact that we have this t equals 0, should I think of it again as the case where I imagine I want to actually prepare a state in the path integral, and then I reduce myself to defining some boundary conditions on the t equals 0 slice. There's really nothing down of it, so t at least 0 is everything the thing knows.
Well, Herman raised this point, right? It's the same point that Herman raised, which is that there could be some pieces of garbage that cannot be prepared by a path integral at t equals 0. And it's a correct comment. There are some rare cases where some pieces of garbage cannot be created by any double hat operator. These theories exist, but I'm not going to talk about them.
Yeah, but these kind of theories are theories where the line defect has to continue forever necessarily.
These are theories where if this garbage did not exist at minus infinity, it cannot be created at t equals 0. It must exist all the time. This doesn't happen in magnets or simple systems. It happens in some exotic theories. It happens it happens in gauge theories with a one-form symmetry, where some pieces of garbage are really not part of the Hilbert space and they cannot be created in any way. But I'm not going to talk about such things.
But the remark about, like, should I see this as distinguished from the Hilbert space states?
Yes,
or should I think of this O hat as exactly talking about
this?
The Hilbert space?
This I would say is not part of the Hilbert space. If you want to be like pedantic, I would say that these operators O hat and O double hat are not part of the original Hilbert space. I introduced them by adding a Hamiltonian on the impurity, and the impurity may have its own Hilbert space. So the full Hilbert space maybe is the tensor product of the QFT and some impurity Hilbert space. So all these operators, O hat and O double hat, they create something that didn't exist before. So I would say they are local operators, but not in the original theory.
Okay, so the point is, when we prepare a state, since it's a tensor product, whatever we will do on the first system will be G-preserving, whereas this O hat is the operator associated to creating a state in the second part of the tensor product.
Yeah,
and that may be
O double hat kind of creates.
So we basically recast this exactly in the quantum
O double
mechanics.
hat just creates this. All of a sudden, at t equals 0, it changes the Hamiltonian to that. That's what O double hat does. It changes the Hamiltonian suddenly. And this may sit in a projective representation. That's what's interesting. This leads to some theorems that I'll show you.
Right. And so this is exactly the 0 plus 1 picture.
So the interesting thing is that the operators that live in that full system are in a linear representation, but the operators that create the impurity could be projective representations. That has some deep consequences. I'll show you.
Thanks.
Okay, any more? Okay. So, to make the discussion, my notes? To make the discussion less abstract, we really have to talk about an example now. I want to show you an example. Otherwise, this discussion is going to be way too abstract. So I'll show you an example which is not a gauge theory. There is nothing to worry about gauge invariance. It's just a very simple scalar field theory where this phenomenon happens. So let's consider the following model. It's in 2 + 1 dimensions, as everything I'm going to say. And it will have 3 scalar fields. It's a model of 3 scalar fields with a nice SO3 symmetry that rotates these 3 scalar fields. It's just the theory of Landau-Ginzburg theory of a magnet, okay? Nothing sophisticated. And we have a kinetic term. So I'll just write the Hamiltonian. This is a quantum. You should think about it as a quantum Hamiltonian. So this is the space derivatives. Then there is the time derivative. Maybe I'll put a half for good measure. Oh, so this is just the kinetic term of 3 order parameters with SO3 symmetry. Just to make this model natural, I'll also put a quartic interaction. I'm not specifying the coefficient, doesn't matter. It flows somewhere. And then there is a possible mass term, which could be negative or positive. So this model has several phases. If the mass squared is positive, it's gapped. If the mass squared is negative, it breaks the symmetry and you get a magnet. Okay, this is just the standard Landau-Ginzburg theory for a magnet. And where is the impurity? So the impurity is going to be a new coupling constant, H, which does so where you do the following funny thing. Unlike the rest of the Hamiltonian, it's at x equals to 0. So we take the quantum field phi a at x equals to 0, and we dot it into a spin operator. That's called the boson-Kondo problem. What is this S? S is an operator that acts on a qubit or a triquet or something, some representation with dimension 2s + 1. So the physical picture is that we have just a magnet, and at the origin we put a Hilbert space with 2s + 1 states, just a spin S representation of SO3. So this operator acts on some external qubit or external atom. It could be some external atom that we put into the magnet, an external atom of a spin S of SO3. So this is always transforming under SO3. It's in the adjoint. These are the spin operators. For spin a half, these are the Pauli matrices that act on the qubit. For spin S, these are 2s + 1 times 2s + 1 dimensional matrices. And they just couple to the magnet order parameter, phi a. So we just couple the order parameter of the magnet to the direction of the spin of some atom. And the spin of this atom could be some large spin with Casimir S times S - 1. Is the setup clear? This is the problem. It's called the boson-Kondo problem. And there is a lot of interest in what does it do as a function of the representation S and as a function of the coupling H. Is it relevant, irrelevant? Okay. So the physical picture is that just an external atom in a quantum antiferromagnet or some line defects in an ordinary magnet. Now, for high energy physics, maybe the Hamiltonian is not so convenient. You can write a simple action. So let me just write the action. So the first piece of the action, d2x, d2t, is just the same as the SO3 quantum field theory. It's d phi squared plus phi to the 4 plus m squared phi squared. I'm just writing very schematically. That's boring. And then there is the new coupling H, where we couple some spin S representation to the order parameter. And that's where it's a little bit interesting. So I'll just write the Lagrangian carefully now to explain how to write an action and do perturbation theory if you so desire. So there will be some new degree of freedom Z, which is like an internal degree of freedom of this external atom. And there is a time derivative. It's a first order action in quantum mechanics. And then the field phi A at x equals to 0 interacts with Z dagger Pauli matrix Z. And we sum over A from 1 to 3. And Z is a Z1, Z2. That's called the coadjoint orbit, if you're an aficionado. You just take two complex variables, z1, z2. You write a first order action. And the claim is that this describes a spin S representation that couples to the order parameter. Where does the spin enter? So z dagger z is 2s. You have a constraint. You have a constraint on the magnitude of these two complex numbers. And finally, these variables z, which are the coadjoint orbit variables, they have an internal gauge symmetry, just because it's a redundant description of a spin S. You can describe a spin S qubit however you want, or a spin S degree of freedom however you want. That's just one way. And that way, we also have a gauge symmetry, where Z goes to itself up to a phase. It's just this description of a spin S atom is known as the coadjoint orbit of SO3 or SU2. It's just a very convenient thing to do if you want to do perturbation theory. Sorry, the coupling H is here. This is actually 1, and it cannot be changed. Okay, now I wanted to explain why does this give a spin S thing? First of all, it's a first order kinetic term. So it has a finite Hilbert space because of that. So this means that the space of Z's is a three-dimensional sphere. The gauge symmetry means that we have to quotient the three-dimensional sphere by U1, and we get a two-dimensional sphere. So this essentially describes a particle moving on a two-dimensional sphere projected to the lowest Landau level. That's why the kinetic term is first order. And that space of states is just a spin S representation of SU2. So this gadget does exactly that and nothing more. Okay, so that's the action of this boson-Kondo problem if you want to have an action. And finally, you can also think about it in a completely different way as a Wilson line. Though there is no gauge field, this is a very simple line operator. You can say, I don't want to hear about this term in the Hamiltonian. I don't want to hear about this. I just want to use the ordinary action of the SO3 magnet. And in that language, it's just a Wilson line. It's the trace of the exponent, pass-ordered exponent, very importantly, of dt phi a times SU2 matrices SA in the representation with 2s plus 1 dimensions. So it's exactly like a Wilson line. You've seen the formula for a Wilson line, maybe in graduate school, AATA. Maybe I'll call it TA. So these are SU2 matrices. It's exactly the same, except instead of a gauge field, we have a scalar field. So this is like a Wilson line for the poor people that don't want to do gauge theories. It's a poor man's version of a Wilson line, where you don't have gauge fields. So to solve the boson-Kondo problem, you have to understand the expectation value of this Wilson-like line for scalar fields. And for that, you can do the Dyson expansion. Anything you know about Wilson lines, you can use. And that's more like an action principle. And this is more a condensed matter approach. And they are all the same. Is the problem clear? So what do people want to know about this model? What we want to know about this model is the following. So I'll just draw the question, and that will be the end for today. You'll have something to think about during the evening. So as a function of m squared, the magnet has several phases. So here it's gapped and trivial. That's what's called the paramagnet. Here we have a symmetry breaking. There is SO3 broken to SO2 from the condensation of the order parameter. And therefore, you have Nambu-Goldstone bosons living on the two-dimensional sphere. And here there is a fixed point, a CFT, which is the Wilson-Fisher SO3 fixed point. And in all of those phases, we have inserted the defect. We have inserted this piece of garbage. And we want to know what's the long-distance limit of this piece of garbage. Is it detectable from far away? How does it affect the magnetization? How does it affect correlation functions? So in all of those phases, we want to understand what's the long-distance limit of this piece of garbage, this atom. Is it going to be affecting the magnetization? Is it going to be affecting the energy density? All sorts of questions like that that are easily measurable. What about the magnetic susceptibility? So you want to understand what's the long-distance limit in all of those three phases. And tomorrow, this is an open problem for at least 30 years. as a function of this. You want to do it as a function of the spin S of the atom, which is a parameter in all of those descriptions. So in the Wilson line description, the parameter S is in the trace. It's in the size of these matrices. In the Hamiltonian, it's the size of this representation. And in the action, it's in the constraint on the bispinor norm. So S is a parameter, which is a half integer in all of those descriptions. This is a half integer in all of those descriptions. And you want to know what's the answer. So tomorrow, I'll show you that just using the projective representations that appear in this problem, we will be able to prove that it's not screened at the fixed point. Namely, it has a non-trivial long-distance limit. So that's a striking prediction for this thing, using anomalies, essentially. We will prove that here it must be detectable far away. It leads to some correlation functions that are altered, and it's not screened. Okay? So tomorrow we'll analyze the projective representation of this problem and the long-distance limit. Okay, I'm done. So.